Okay, let's get started, please. So today we're going to be talking about something pretty important. It's called the Lagrange Multiplier method. Lagrange Multiplier. Okay. So the problem is going to be something like this. You have some function, so you have some function from R2 to R. So you have some function here. Okay, so from R2 or Rn, like R3, whatever. Okay, and you have a level surface of that function. Okay, so you have some S of h, and this is going to be the level surface x in R2 such that g of x is h. Okay, and then you have some other function. Then you have some other function f, right? And f is also f is on R2. Is also on R2. And you're wondering, the question is, where is f biggest or smallest when constrained to that level surface? Okay, so here's the level surface, right? The level surface is this one-dimensional thing, right? It's basically a one-dimensional thing that lives in the plane. So like last time when we were talking about maximizing and minimizing, we were saying, well, you've got this function that's defined on the whole plane, right? But now we're doing something different. We're not looking at functions that are defined on the whole space, but on functions that are defined on something of lower dimension that lives inside the space. Okay, right? Do you see what I mean by lower dimensional? Right? This is not in any way a two-dimensional thing, right? It's this surface, or like if I were in R3 and I have some sort of sheet, some sort of sheet in R3. I've got a lower dimensional thing that's living inside there. So, right, and you're wondering, you say, okay, we've got this function, and let's look at it not on the whole space, but rather constrained to this level surface, and see where it attains its maxes and mins. So you want to optimize. Okay. So you might remember last time at the end we had something exactly like this. You had we had some function g of xyz was 2xz plus 2yz plus xy, right? And we had some other function v, which was xyz. And we got this from the problem that was, you had a box, you were going to make a box, and the amount of material, a box with no cover, with no top, and the amount of material had to add up to 12, right? The amount of material was constrained to 12. So this function had to be equal to 12, right? And you're trying to maximize the volume. Well, the volume is x, y, z, right? Where x and y were the length and width, and z was the height of the box, right? So this is exactly this sort of problem, right? You've got this. Both of these guys are functions on x, y, z. Both of these guys, g and v, are on x, y, z, and you've got the level surface of g at height 12. Right? You've got some sort of surface here, and you're wondering where is v biggest when it's constrained on this space, right? And it turned out to be like 2, 2, 2, 1. Right? The dimensions had to be 2, 2, 1 to maximize. If we had maximized this thing over the whole space, what would be the answer? If if we had maximized this thing over the whole space, what would have been the answer? Where's the maximum? Sydney? There is no max. Yeah, there is no max, right? Because you can just make you can just make larger and larger boxes, right? If you're not constrained to how much material you use, well, there's no limit on how big a box you can make. Okay, so and I hope you're seeing the difference between the non-constrained problems and the constrained problems. Okay, non-constrained problems, if we do it, we just use our first derivative test to look for critical points, et cetera, right? If there are no critical points, then So non-constrained problems, just use your derivative tests. For constrained problems, however, you can't do that anymore, okay? Because we're not on space. We're on something that lives inside the space. Okay, that really depended on us being on the whole space. Okay, so instead we have to think about it. So what kind of method? It will turn out that what we need to do is to find the place. We'll see that x gemma, that's to say maxes or mins, occur where the gradient of g is parallel to the gradient of f. Okay. It will turn out that those are the places that we need to look, where the gradient of g is parallel to the gradient of f. Okay, everyone okay? I haven't told you at all why this happens, but here's the setting, and here's the method right here. You look for where the gradients are parallel. Any questions so far? Let me ask you a question. What do we know about the gradient of g? Here's a level surface.
Always perpendicular to the function straight on the level surface.
That's right. So remember, for functions, if you're looking at a function, if you're looking at the gradient of a function on that function's level surface, then the gradient's going to be perpendicular, right? So we actually know something about the gradient of g already. At each point, the gradient is perpendicular to the surface, right? But it could be pointing inwards, I don't know. But right. So at each point, you've got this thing. So the gradient is perpendicular. Gradient is perpendicular to the surface. Okay. So so here's what we're going to show. So let me set it up. So what we need to show then is that wherever f reaches a maximum value, it is perpendicular to the surface. Right? Wherever f reaches a max or min on the surface, it's going to be perpendicular to the surface. Right? If we show that, then that'll tell us that whenever these guys are perpendicular, that's a possible place for a max or a min. Everyone see the strategy? We know already that the gradient is perpendicular to the surface. Right? At each point, the gradient, right? Gradient vectors, gradient of g at this point is going to be perpendicular to the surface. Gradient of g at this point is going to gradient of g we know is perpendicular to its level surface. You remember, what we said about the gradient, that the gradient tells you what direction to go to increase fastest, right? And perpendicular to that, you won't be changing at all, right? So here, going perpendicular to it, you're not going to change at all because it's a level surface, right? So remember, the gradient is perpendicular to the surface, and what we're going to see is that any function that attains a max on the surface at some point is going to be perpendicular to the surface too. So this completely unrelated guy, as long as he attains a max or min somewhere, is also going to be perpendicular to the surface, and so that gives us the method. So let me write it again, right? So you have g, a function from R2 to R, It's a continuously differentiable function, and S of h is the level set at height h of g. Right? So recall that gradient of g is perpendicular to the level set. Okay. Actually, let me leave that part out because that's not really part of the study. But it's true. So you have some other function, f from R2 to R, also continuously differentiable. And you suppose that f, when constrained to the level set of G, attains a max somewhere. At some point on the level surface. So here's the level surface again, SH, and at some point, F attains a max. Right? So this is the level surface of G. Right? And at this point, F attains a max. Or min, whatever. Okay. Then the gradient of f at that point is going to be perpendicular to the gradient of g at that point. So that's our claim. At that point, the guys are going to have perpendicular gradients. Okay, so let me explain why this. Let's think of why this happens. Why? We already know that the gradient of g at x naught is perpendicular to s there. Right. That we know from before. So it suffices to show, let's show that the gradient of f at x naught is also normal to s. Okay. Is also perpendicular to s. Okay, and the argument goes along the same lines as before. Take any curve gamma that goes from R into SH. Okay, so here's S of H. We set up such that gamma at time zero is that point x naught. Okay. So here's the point x naught, right? Our function f goes here, like this, and we're creating a curve gamma that at time zero runs through here. So this curve, just runs on the surface here. It runs on the surface here, but at time zero it passes through this point x naught. Okay. So it's running around on the surface. It doesn't. This thing is sitting in the plane, but it doesn't leave that surface. Okay. It always stays on the surface. Okay. Right. Okay. What can we say about the composition f composed with gamma? What can we say about f composed with gamma?
It's f of gamma at 0.
certainly at time 0, we're going to get f at x0. Paul, don't say. I mean, don't blurt out. But raise your hand, please. That's it. Right. So that's true. What else? So does that tell us anything, or well, make some observations, about f composed with gamma. I'll make a dumb observation. It goes from R to R. Okay. Paul's made a better observation that at time 0, it hits this value, f of x naught. Anyone have anything else to say about it? Flo.
It defines all the points on F that are within the level surface. The level surface is described by gamma.
Okay. Actually, that may not be true. If we were on a surface, then all gamma is just a path that's running through that point. Okay, so not necessarily true. Just to clarify, this thing in the middle really should be Rn. And gamma is a path. Gamma is a path that's running on this surface that passes through x naught at time 0. Okay. Is there anything? Anyone have anything else to say? Peter?
Is the gradient of g equal to the gradient of f times gamma?
No, not necessarily. Right? G is just the levels. G is just the function that defines the level surface here. So the relation between g and f, there is basically no relation between g and f. Yeah. But except for the relation we're about to point out. What was x naught? What was x naught? What was special about x naught?
It's for an extreme value.
It's where the extreme value occurs, right? So what does that tell you about the composition? Can you think about it for a minute? Just gonna walk around.
If you plug in the x of the extreme is, it gives you that doesn't matter.
Do you want to figure it out? What can we say about f composed with gamma, right? Well, at time 0, it hits this value f of x naught, right? What do we know about f of x naught? F of x naught is the max, right, for f, right? So what does that tell you happens at time 0 for this guy?
That its slope equals 0.
The slope will be 0 there, right? This thing attains its max at time 0, right? Because the maximum value you can get through f happens at when f is evaluated at x naught. That's to say, when the time is 0. Right? Do you guys see that? Right. Here you have this function. Here you have the level surface, right? F. Right. At this point, f of x, f reaches its highest value, right? Now you've got this curve guy that goes into here, right? At time 0, right? We're looking at the composition, right? And we say, oh look, at time 0, we're going to, right? At time 0, we get the maximum value you can get through f, right? Well, that tells us that this guy attains its max at time 0, So this, right, this guy goes from R to R, oops, R to R. We see that f prime, I'm sorry, f composed with gamma attains a max at time 0. Right? And that tells us that its derivative, right? Its derivative at time 0 is 0. Right? But using the chain rule, we see that this is going to be the gradient of f at gamma dotted against gamma prime is 0. So by the chain rule. We see that the gradient there dotted against gamma prime is 0. In other words, gamma of f at x naught is perpendicular to the tangent vector of gamma at gamma 0. I'm sorry, at time 0. At t equals 0. Okay, so let me draw the three-dimensional picture, which will make it better. Here is x naught. Gamma is some path that cuts through here, right? At time 0, it goes through here. Here's f. Okay, and gamma prime is going to be some tangent vector. This thing here is gamma prime at time 0. Okay, right, here's the curve of gamma. And here's gamma prime. Okay. Now we could have done this for any gamma, right? This happens for all such curves gamma. So if I ran another guy this way, then the gradient vector is perpendicular to that guy's tangent vector. Right? If I run a vector, right? So if I get another tangent vector, right? I get another tangent vector. The gradient of f at x naught is perpendicular to all those tangent vectors, right? Right. Gradient of f at x naught is perpendicular to all tangent vectors, all such tangent vectors. And so is perpendicular to the surface itself. Okay. Just in the same way that we saw that the gradient of the level surface, was perpendicular to all such tangent vectors, we see that the gradient of this function, which attains a max there, is also perpendicular to the surface. Do you all remember how we showed that the gradient of g was perpendicular to the surface? G was a function that's constant on this surface, right? So if we looked at g composed with gamma, then that was just constant, right? And then when we differentiated it, we saw that these things were perpendicular, right? This gives you that the gradient of g at gamma of x is perpendicular to gamma of x, gamma prime of x. Right? That this dot this is 0. That's 0. Right? And so this is what we're saying here is that it need not be constant, but at any place that the function attains a max, well then it's going to be perpendicular also. Ask questions if anything seems confusing. So here's the sketch, right? We already know that the gradient of G is perpendicular to the surface at each point. We know that f attains its max at some point on the surface. And so we run a curve through there. We run a curve through there, that curve, which passes through that point at time 0. Because f reaches its max at that point, that tells us that the composition reaches its max at time 0. The composition reaching its max at time 0 tells us that the derivative at 0 must be 0. By the chain rule, that tells us that the gradient of the function is perpendicular to the tangent vector of that curve. The gradient of the tangent vector is perpendicular thus to all tangent vectors, and thus perpendicular to the surface. Is there, if there's any, I'm not sure if people are confused, but if there's some point where you can figure out, like, I didn't understand from this to this, that's useful. Yeah, Laura.
Can you
Yes.
repeat, please, from like, I forgot which part. I think f composed with gamma attains a max.
Yeah. So f composed with gamma is this function from R to R, right? At time 0, its value is going to be equal to that of f at x naught. But f attains its maximum value at x naught. So that tells us that this guy attains its maximum value at time 0. Is that part okay? Okay. And then you say, okay, I have a function that I have a one variable function from R to R. It attains a max at time 0. That tells me that its derivative is going to be 0 there, right, from calc 1. Okay. And then suddenly calc 3 comes in. You're taking the derivative of a composition of functions, right? Gamma goes from R1 to Rn. F goes from Rn into R1, right? And so the composition is going to end out to be equal to, the derivative of the composition will be the dot product of the gradient vector against by the chain rule, will be the dot product of the gradient vector against the tangent vector. And so that tells us that the gradient vector dot the tangent vector is 0. In other words, the gradient vector has to be perpendicular to this tangent vector, right? But it's perpendicular to all tangent vectors, and so it's perpendicular to the whole surface. Okay, Alana.
How do we know that it has a max at x naught?
That's given to us, right? That's part of the setting, right?
Is that always true?
That's so. What we see from this is that wherever f has a max, it's going to be perpendicular to the surface.
Okay. So
The gradient's going to be perpendicular.
We're just calling that x
Yeah.
naught.
So what we see is that conclusion, right? Wherever f attains a max or min on this level surface of G, the gradient of f will be perpendicular to the gradient of G. Yes?
So
Linda?
in the homework problems, we're not going to be given the maximum, we're going to be asked to find it using this.
That's right. And we'll do it by just taking gradients and seeing where they're perpendicular to each other. Right? These are the analogs of the critical points. These are the possible places for the maxes and mins. Say, look at gradients, see where they're perpendicular. Oh, okay, they're perpendicular here. Let's check those points. Whichever one is the biggest, that will be the max. Whichever one is the smallest, that will be the min. Okay, so let me show you how this works. How you use this. Okay, so so to find extrema of f on S, it suffices to determine where gradient of f is perpendicular to gradient of G. In other words, where the gradient of f equals some multiple of the gradient of g. Okay. People usually use this letter lambda, some multiple of g. Right? Being parallel means that one is a multiple of the other. So this guy is a multiple of the other guy. Okay. So you have this multiplier. It's called the Lagrange multiplier. So this is So let me do a couple examples to show you how it works. You have xy equals 1, and you have some other function, f of xy is x squared plus y squared. So here's your surface, right? Xy equals 1. So it looks like this, right? And you're wondering, you have this other function, and you're wondering where it's maximized or minimized. Okay. I mean, you can sort of tell by looking at it that it's not going to have a max, right? Because as you head farther and farther away, you're just going to get larger and larger numbers. So it's not going to have a max. So really, what we're looking for is where this function is minimized when constrained to the surface. The question is, where is f minimized when constrained to the surface? Okay, so this thing here is your g, right? This is your g of xy, right? The function that defines the level surface, right? You're setting it at a height of 1, right? Okay, and so the game is, right, you just take gradients, right, this will be 2x, 2y, gradient of g is going to be y, x, right? And so what we want is our conditions then become that 2x, right, 2x, 2y, you want to be some multiple of y comma x. Right? And you want xy to be equal to 1. That is, 2x should be lambda y, 2y should be lambda x, and you want xy to be equal to 1. So, basically you start off with a bunch of conditions that are given to you by the theory, and then you try to figure out what x and y have to be. Okay, and this from here on, it's sort of like by hook or by crook. Whatever you do, you try something or other and see if you can figure it out. So for example, you could say, oh, let's see, I'm gonna divide this by. So I'm going to divide this thing by y. So 2x over y is lambda. I see that 2y over x is also equal to lambda, right? And so that tells me that 2x over y equals 2y over x. Okay. So that's one thing we could do. You could do something else, but that's what I chose to do. Okay. Okay. And that's okay to do. It's okay to divide by y and to divide by x because we know that we're constrained to xy equals 1. So neither of them could be 0. So notice that xy equals 1. So then solving for lambda, we see that 2x over y equals 2y over x, right? Which tells us that 2x squared is equal to 2y squared, which tells us that x squared equals y squared. right, that tells you that x and y are either, well, using the fact that xy equals 1, since xy equals 1, right, that tells us that x and y are going to be, you know, plus or minus 1. Right, these guys have the same size, right, and they're right. So we know that the size of x and the size of y are the same. The size of x and the size of y are the same, and we know that xy equals 1, right, which tells us that the absolute value of x times the absolute value of y is equal to 1. Right. And they're the same size, and so you see that xy must be plus or minus 1. Both positive or both negative, right? Since xy equals a positive 1. Right. So what we get is that 1, 1 or negative 1, negative 1 are possible locations. Of the minimum. Okay. Right, and what we see is that these both turn out to be minima. F is 1 there, and that's the smallest of them. I'll do another one. Maybe that will. Well, any questions first on any questions? Yeah, I should stop.
How did you get that they were both 1? Like the value of the function was 1?
Well, I know that they're going to be plus or minus 1. X and y are going to be plus or minus 1.
No, I mean the minima, like the value of the minima.
Oh, so I'm sorry, it's 2. It's 2.
Okay.
Right, sorry. F of x was x squared plus y squared. So the value is 2 there. Sorry.
Okay.
Sorry. That was just wrong. Other questions or corrections? Let me do another one, which is, so I was planning to do this one first, but let's see. So here is one. So sort of the opposite of what we were doing before. A of xyz is 2xy plus 2yz plus xe. Okay, so minimize this thing under the constraint that v of xyz is 4, okay, where v is just the product x times y times z. Okay, so maybe take a minute and set up the conditions. Okay, just write down what facts you're going to have about x, y, and z. Okay, turn to somebody next to you and just say, well, the conditions are this.
So it's 2x plus 2y.
Just working on the last one. So
Well, you
G
make
equals
Here's the gradients. I figured it was the- I know it's gradients.
A is 2y plus
So you make two gradients. Each term is this term, x, y, z equals 4. I'm not sure. 4 variables.
You just gotta send them to each other to do.
I do not want to choose that else.
Although I think if we use Lagrange, lambda, yeah.
Okay, right, so you take the gradients of each guy and you say, okay, I want these guys to be perpendicular to each other. Okay. So you say, okay, well, that tells me that lambda yz is going to be 2y plus z, lambda xz is going to be 2x plus 2z, lambda xy is 2y plus x, and I also have this last constraint condition that xyz equals 4. So those are all the things that's all the information we have, and then we work it out from there. Okay. There are a couple ways you could do it. One, you could, just as we did before, solve for lambda by dividing by by yz, by xz, and by xy. And it's okay to do that, again, because we know that none of them are equal to 0. Okay, right? So you notice xyz equals 4, so none of these guys are 0. It's okay to divide by them. Okay. So solving one way, solving for lambda, we get 2y plus z over yz equals 2x plus 2z over xz equals 2y plus x over xy. Right, that's to say, we break it up, 2 over z plus 1 over y equals 2 over z plus 2 over x equals 2 over x plus 1 over y. Right? Ethel.
How did it do
Did I make a mistake? Let's see. So I'm just separating these things, right? Here I've got 2y over yz. That's 2 over z. I've got 1 over y. Right, just fractions. Right? Okay, so what does that tell me? That tells me in particular that look, if I compare the first guy and the last guy, right, that tells me that z and x are the same. Right? Z equals x. Or if I compare, say, this one and the first, if I compare the first two, right, then I see that 1 over y equals 2 over x. That's to say, x is equal to 2y. Right? If I compare the first one and the third one, then I see that x equals z. X equals z. Right? Because I get 2 over z equals 2 over x. Right? So x equals z. Right? And that's enough, right? At this point we know that the thing is going to look like 2y, y, 2y. Right? Because x and z are the same, and x is 2y. Right? So wherever this thing, these guys are going to be perpendicular at such a point. Right? At this point, Is everyone okay with that? Any questions? Any questions? Right. So, right, we set up the conditions. We solved for lambda. We said let's let lambda. I mean, lambda is the same thing. So all these guys are equal to each other because they're all equal to lambda. And then we use fractions and just divide to get this form. Right. And then we just use them in pairs to get information about the individuals. Okay. So then we say, okay, well, the only thing we have left we haven't used is that xyz is equal to 4, right? That tells me that 4y cubed is equal to 4, right? xyz equals 4. xyz is equal to 4. 4y cubed is 4. Y cubed is 1, and so y is 1. Right? And that tells me that 2, 1, 2 is it. Right? 2, 1, 2 is where the minimum occurs.
And you know it's minimum, not in maximum, just because like the question said minimize.
Yeah. Yeah. Yeah, basically. Or yeah, Paul.
So then if it was just find maximum or minimum values and there's like critical points, then you would just do what we did in like 15.7, right?
Yeah, basically.
Check.
Yeah. So it's a little bit, in some sense they have to, for these problems, they sort of have to tell you what you're looking for, to be honest. If it's a closed surface, closed surface, say, if it's something like this, like if your constraint is to like some closed and bounded surface, but you don't know what closed is. But anyway, these things are closed. Okay, some sort of closed and bounded surface, then you're guaranteed to have a max and you're guaranteed to have a min. And so you'd say, okay, let's find out where the guys are perpendicular to each other, and you get a bunch of points. Okay, you get a bunch of points, and you'd say, okay, I know there is a max or a min, there is a max and there is a min, and it has to lie with one of these guys. So you just evaluate the function at each of the things, and the biggest one will be your max, and the smallest one will be your min. Okay. So if it's a closed and bounded surface, then that's how you do it. You say, I'm going to find the places where it could happen, and I just evaluated each one. The biggest one is by definition the max. The smallest one is by definition the min. Okay. For these things, however, the surface is actually unbounded. So you don't have this guarantee that there's going to be a max or a min, and so the problem really should tell you that what you're going to be looking for. Okay, so that's, yeah.
But then unbounded, that's when you use 15.7, like that, where D is greater than.
No. You're still gonna use this. You're still gonna use this. Yeah, you're still gonna use this. Yeah. Okay. So let me just say one small thing. That we could have gone another direction. I think maybe this is pointed out by a student. Could we do something like this? Lambda xyz is equal to xy plus xz. Lambda xyz is equal to 2xy plus 2yz. Lambda xyz, just multiplied by the missing variable, multiplied by x, multiplied by y, multiplied by z, and set all those things equal to each other. And you get basically the same sort of thing. So as you see,